Okay, so I would like to, as many of my colleagues, I would like to thank the organizers for setting up this very widespread conference, and in particular Jan Huige for giving me the opportunity to talk. This is going to be a talk in which basically I was reminded that in principle the audience that could attend this presentation could be very wide. So the purpose of this presentation is literally just to highlight something that may be very obvious to many of you. So apologies for the experts. There won't be any new results in this talk. But I would like to stress, since the common theme in the conference is the mathematics, the universality of the mathematics behind information theory, so in particular probability theory and things like that. And if I manage to convey anything, I would like to compare a little bit the way in which we describe the information in a classical coin versus quantum mechanics, and mainly with the Unruh effect in black hole physics, if I succeed in doing the time. Of course, a priori, you can already say that the specific details, what physicists would call the degrees of freedom in each of the cases that I have already mentioned are going to be very different. But something that I would like you to keep in mind from the beginning, but I will try to stress, is that the states of the different systems that one wants to discuss, they are not known a priori unless you measure. That's particularly clear in the case of the coin and in quantum mechanics. And that will be the one link that I would like to explore. And in the case of the black hole interior, in the case of the black hole, perhaps it's less apparent. But I would like you to keep in mind that as it has been mentioned in several talks already, that the interior is not classically accessible from someone that remains outside of the black hole. And so in that sense, there is this lack of accessibility to the potential state of the black hole. But one of the lessons is that the mathematics of information is going to be universal. And so if you are interested, like people in my community are interested in developing quantum gravity, and perhaps some of us do not have a clear idea what the rules of the game are, the mathematics of quantum information applied to quantum mechanics can provide some constraints for what we should be aiming for. And that's something that has appeared quite clearly this morning in Bartek's talk. So to begin with, let me just start very, very low key. And, the first question that we typically ask when we don't know anything about how to quantify information is, how am I going to assign a number or what do we mean by information? So if I consider a coin, clearly before the flip, there are two possible outcomes, heads and tails. They may have the same probability if it's a fair coin, or otherwise it's a biased coin. So clearly there is some uncertainty. So the idea that Shannon introduced for information in a more abstract sense than the one that perhaps some other physicists introduce is a quantity that describes either the uncertainty that you have before throwing the coin, or the property that you gain after knowing that it was heads or tails. And it's a standard question to ask whether this quantity is the same one for a fair coin or a biased coin. And hopefully we will agree that if I have a very biased coin, in which I typically always get heads, the amount of whatever I gain when I throw the coin is much less than for a fair one. So clearly that quantity depends on the probability that we assign to the outcomes. So the lesson of this quick discussion is that you have some random variable. That random variable has some outcomes, and those outcomes have associated some probabilities. And what we may call information, which I will start referring to the entropy. So imagine that I pick a single event in this random variable, keep in mind the coin if you want to. I want to assign some function to this space of outcomes. Let's pick one fixed event like E in this slide. And then it turns out that if I require some actions which are rather natural, which is this function here should only depend on the probability of the event. It should be continuous in this probability. And if I consider two independent events, intuitively I expect that such a function should be the sum of the two pieces of information, because the probability factorizes, there is no correlation between them. And then the fourth one is basically just a normalization, basically in which units you want to quantify this function. It turns out that under these axioms, if you want to call them axioms, there is a unique function that satisfies this property up to an overall constant, which has to do with axiom 4 that fixes denormalization. And this is where the...
One quick question, are your slides advancing, or are you just talking about with just your front page?
In which slide are you in?
I'm in slide 1.
Oh, so I'm in slide 4. Okay, so I have no idea why this is happening. So should I stop sharing and try again?
Thanks for the catch, Judge.
Okay, so sorry about that.
They're still not advancing. Here we go.
Yes,
yes.
Okay, I just need to learn. Did it advance now?
Yes.
Oh, okay. So I don't know why it worked now, but okay. Okay, sorry. So this was the coin. Okay, this was the coin discussion, and these are the axioms that I was referring to. So if I focus my attention on a single event, the discussion between the fair coin and the biased coin was to try to point you to the fact that we want this function to be just a function of the probability. If we require this to be continuous, and for independent events, whatever we are looking for splits into the sum, because there is no correlation in how we compute this probability, it turns out that up to this normalization axiom, which is just an issue of units, or if you are more mathematically oriented, the base of the logarithm of the answer, the function is unique, and it gives rise to this log base 2 of the probability of the event. Now, if I want to assign a quantity, so an entropy, an amount of information to the full ensemble, what we do is, this is what Shannon did, we average the entropy of the individual events with the probability of the ensemble. That's what appears in the formula in red, and this is what we call Shannon's entropy. Here I'm plotting, in the case of a binary system like the coin, how the entropy of a single event behaves, and what's Shannon entropy. So here you can see that this function gets maximized for a fair coin, which is at 0.5, and otherwise it's symmetric. Okay, so I will be using either Shannon entropy or entropy indistinguishable from now on. Now, for the people that may have not thought about this, I just want to bring a very trivial example, I hope, on how universal this setup is. So let's consider a toy model. This is really a toy model, in which we are given a game in which there are 4 cells available, and each cell, which are these squares here, can take 2 colors. I've chosen them to be white and black, and I will refer to white as zeros and blacks and ones, but this is just notation. Clearly, there are 2 to the 4 different configurations, because the choice of the location of white and black, I declare it to be irrelevant. And I can order them with this ordered list of 4 numbers. Now, the game that I want to play is that we know that there are 4 cells, but I can only measure the number of black cells, which I'm going to call E, but not their location. So this means that I have some information on the order list, but I don't have enough information to identify what is the precise list of 4 numbers that I am assigning. So let me be more explicit. In the particular case in which the number of blacks is either 0 or the number of blacks is 4, what I call the gray color, which is the number of blacks divided by 4, will either be 0 or 1. And in this case, there is no uncertainty. Everything is white or everything is black. But in any other intermediate situation, so when n is equal to 1, 2, or 3, so the number of black cells is 1, 2, or 3, there is an uncertainty in which microstate, in which order list of the 4 numbers I'm considering, because there is 4 choose E ways of choosing E number of black cells among the choice of 4 cells. So from the perspective of Shannon's description of the system, which is a much more abstract one, you would say, well, what is happening is that there is a subset of configurations which is defined by the number of black cells. And if I can assign some probability to each of them, for the sake of this discussion, let's assign equal probabilities to these degenerate configurations. And then I would be just giving you, in the previous example, I would be giving you a random variable which has a uniform distribution to it. And if I would be able to identify what is the precise configuration out of the 4 choose E that share the number of black cells, the amount of information that I would be able to extract in that case is log dE. What are the lessons that I'm trying to extract from this simple example? What I want you to take home, again, if you have not thought about these things, is that if I give you any system, it may be physical or abstract, it doesn't mind, because Shannon is completely universal, that's part of the point. If I don't have a precise description of the system, which is what I will refer as coarse-graining, I don't have access to all the specific details that identify the precise outcome. So that coarse-graining generates uncertainty, and the way to quantify that uncertainty is through Shannon's entropy. That's one way of thinking about it. Another thing that I want to stress, which perhaps I should have discussed more in detail, but I hope that you find this intuitively, is that if I vary the change of black cells, of course, in my example, everything is discrete, but if I go from one number 2 to a number 3, I could ask, how does the amount of Shannon entropy changes between the 2 cases? And there is a linear relation between the change in Shannon's entropy and the change in the number of black cells. The coefficient that appears in this linear relation is what physicists call temperature. And I'm just trying to highlight that even though this example is extremely simple, this actually happens in every single thermodynamic system that we're aware of in equilibrium. And this linear coefficient is what determines the temperature. So that's precisely what thermometers measure in our rooms. So these considerations are very general. And so what Shannon did was to put the perspective of statistical mechanics and thermodynamics from the perspective of the experts into a much wider mathematical framework. Now, let me move to quantum mechanics. So quantum mechanics, independently of whether you have experience with it or not, can be introduced in terms of a bunch of axioms. So what the physical systems, so for instance, if I give you a coin, but the coin happens to be quantum, I'm going to associate with it some Hilbert space. That's the space of states of the system, just as a point particle has the space of initial configurations or the trajectories associated with it. Here we will talk about a Hilbert space. And the actual states of the system are either normalized vectors in this Hilbert space, because the Hilbert space has an inner product, or density matrices, which are some operators. And all you need to remember about these guys is that they are Hermitian, positive definite, and they have trace equals to 1. If I give you a state, how does it evolve in time? It evolves in time through this rule. Basically, you need a unitary operator. This unitary operator, the connection with the Hamiltonian in physics is through this exponential relation. But the important thing is that unitary operators transform density matrices among themselves. And the reason why it has to be a unitary operator is because unitary operators preserve the norm of this state, or they preserve the trace condition. So axiom 2 is compatible with axiom 1. Now, axiom 3 is typically the trickiest one. So in quantum mechanics, if you want to know anything about your system, you need to perform a measurement. and I need to tell you what a measurement is. In a nutshell, a measurement is a collection of operators that are defined, that are acting on your Hilbert space. So it's a collection of linear maps, homomorphisms in that Hilbert space. And what I'm requiring them is that they satisfy this resolution of the identity. This is again because of probability considerations. Now, what do I measure? Well, what I measure is this label, small m, labels the different outcomes of my measurement. And if I happen to measure the label small m, the probability that I actually obtain that measurement is given by axiom using this trace in the Hilbert space. The last axiom involves relating the Hilbert spaces of individual quantum systems with composite systems. So think of this axiom as I give you n quantum particles, for instance. Each quantum particle by axiom 1 has one Hilbert space. Let's call it H1, H2, and Hn. We could ask the question, what is the Hilbert space associated with the composite with the composite system of n of them? And the answer is the tensor product of them. So sorry for going so quickly, but the mathematics, actually, I will be working in finite dimensions as much as I can. So if you come from mathematics, this should be hopefully easy to retain. Now, what I wanted to achieve in this slide is to consider the easiest possible example of a non-trivial Hilbert space. This is C2, and it describes what quantum information theories or physicists would call a single qubit. Here I'm writing a general vector in this Hilbert space in some computational basis, which I have denoted 0 and 1. This is an orthonormal basis. And the general state is a linear combination because a Hilbert space is a vector space. And since the states by axiom 1 are normalized, these complex coefficients need to satisfy this identity. Now, because of the continuity of these alphas and betas, there is an infinite number of such vectors. So you may be worried if we think in terms of the coin where we had only two outcomes, heads and tails, you may be worried that there is an infinite amount of information that we may assign to this vector. Now, what I wanted to convey in this slide is that in our classical assumption, there were a couple of hidden assumptions, if you want to phrase it in that way. One of them is that no matter how many outcomes we have, we are able to distinguish perfectly among them. And that when we look at an outcome, we actually have a perfect technology to do that. Now, what I want to start stressing from now on is that one way in which we can associate information in quantum mechanics is through the accessible information that an observer has through measurement. Notice that axiom 3 is the only way that the theory tells us of extracting information about this vector. If you don't measure it, you will never know it. And the observation is that even though this state depends on these parameters alpha and beta, the truth is that I can come up with a measurement, which I have just written down here for you. It's a projective measurement that can identify this vector uniquely. So the first remark to keep in mind is that we will try to assign some notion of quantum information through accessible information to the observer through measurements. So I need to perform a measurement. And the other one has to do with the fact, sorry for not proving this, that non-orthogonal states can actually not be distinguished in quantum mechanics. That this has to do with the no-cloning theorem. And so it means that whatever notion of quantum information we come up with, there may be subtleties or new consequences. Now, typically there are two features in quantum mechanics that we typically like highlighting. One of them is the linear superposition aspect of it. And the other one is entanglement. In this slide, I'm trying to tell you in a very toy model, so qubits, how we can generate these things in a very natural way. So imagine that I start with 2 qubits. This is 2 copies, so I'm using axiom 4, 2 copies of my previous qubit discussion. And I start with an state, which is the tensor product of 2 elements of the configuration basis. If I act on my first qubit, which is labeled with A for Alice, let's say, with this matrix, with this operator, which is so-called Hadamard gate in the literature. Notice that this operator is only acting non-trivially on Alice Hilbert space. I'm doing nothing in Bob. This is the identity. This is a way, the result of this operation is to generate a linear superposition. So I'm going from something that was not a linear superposition to something that is a linear superposition. And these things can be implemented technologically in a lab. So this is one way in which we can generate linear superpositions, for instance. There are many others. But perhaps what I wanted to highlight more importantly in this slide is that if instead of considering an operator which is only acting on a subspace of my Hilbert space, which is a single qubit, if I consider an action that acts non-locally, meaning this is a 4x4 matrix that is intertwining non-trivially one qubit with the other, such as this C0, when this operator acts on this linear superposition state that I had here, I end up with a state which is in red. This is an example of a Bell state. But what is important is that if we would have the time and we would try to prove whether this state can be written as the tensor product of two vectors in Alice and Bob Hilbert space, this is impossible. Whenever this happens, we call these states entangled states. Now, in the classical discussion, I tried to put some minutes to convey the idea that coarse-graining generates uncertainty, and therefore it generates Shannon's entropy. I really wanted to share with you how precise and how intuitive that thing is in quantum mechanics. That's why I'm going over all this discussion. So let's consider an arbitrary, the tensor product of two Hilbert spaces. So I'm giving you a quantum system and I'm dividing it into two subsystems. But let's ask the question, okay, imagine that Alice is in Mars, Bob is in Edinburgh, and you are working with Alice in Alice lab, and all you can measure are operators that have support in this subspace of the composite Hilbert space. The question that I want to ask is, how does that observer, someone in Alice's lab, describes the predictions of quantum mechanics? According to our axioms, I can start with any state. So let's consider this state. This is a linear combination of my favorite configuration basis of zeros and ones. And A and B are complex numbers which are normalized. Our axiom 3 uses the inner product in the composite Hilbert space to compute the expectation value of this operator. So I'm using the axioms. There is nothing new yet in this story. And when I use the axioms, I get this answer. I want to point out, even though mathematically this is kind of trivial, that the answer factorizes into two kinds of factors. The one that you can see highlighted by my factor, by my cursor, sorry, which is in black, is the inner product computed in the Hilbert space of Alice system that depends on the details of the operator MA. And then there is another coefficient which looks like a classical probability, just the complex, the norm of this number is square and the norm of this number is square. Now, please notice that this is true for any operator MA. It doesn't matter which operator you decide to measure. I'm assuming that it's self-adjoint, of course. So the mathematical question is, can I write this expression, which was defined in the composite Hilbert space, the total Hilbert space, can I write it entirely in terms of quantities that only have support in Alice Hilbert space? This defines for you this red quantity, which I will refer to as a reduced density matrix. And it turns out that the answer to this mathematical question is given by this quantity here. This can be obtained by taking the trace. This is what physicists call integrating out Bob's Hilbert space. You take the trace over whatever information you had in Bob's Hilbert space of this projector, which is a projector that you construct out of the initial state. And the outcome looks like, no, it's a self-adjoint operator. And it contains a superposition of a projector in the 0 state and the 1 state. But these coefficients here are really like probabilities of in our coin at the beginning of this discussion, even though I'm doing quantum mechanics. So this is the closest, in some sense, that you can describe classical coins in quantum mechanics. The lesson from this discussion, apologies if I didn't explain this well enough, but this is very important, is that the guys that are working in Alice's lab, the measurements that they can perform, which are given by this answer here, they really behave like ensemble. They see an ensemble. Now, one way of quantifying the amount of information associated with that ensemble, so an ensemble is like a random variable in the classical discussion, is proceeding by analogy. So Shannon computed the trace of the probabilities, log probabilities. Those probabilities are now the eigenvalues of some operator, which is this density operator rho. So von Neumann defined the so-called these days von Neumann entropy as the minus the trace of rho log rho. It's much more difficult to justify axiomatically this quantity, so I'm proceeding by analogy. But I just want to highlight two important examples. If I consider a pure state, the von Neumann entropy is 0. This reflects the fact that there is a measurement that identifies this state with certainty. So there is nothing to be gained. There is no uncertainty in the sense that if I give you some density operator, which is a collection of rho I states with classical probabilities pi, the von Neumann entropy in this case will give you non-vanishing quantum information. So it's important to distinguish the two, and this is what accessibility to information, this is the point I wanted to convey. Now, to stress how surprising entangled states should be from the perspective of information, let me highlight that if I go back to my system of 2 qubits, there is a basis of states, which are the ones that are defined here. So you can check that any vector in this Hilbert space can be written as a linear combination of this. Now, construct a projector to each of these pure states. These are the projectors. If you sum them, they give you a resolution of the identity. And so this means that this defines a measurement for you. So if you are given 4 states, the 4 Bell states, and you don't know which one it is, when you do a measurement, you will know with certainty which one of the 4 you were given. So in that sense, any of the Bell states, which is a pure state, doesn't carry any information. On the other hand, if you take any of such states and you only do measurements in Alice Hilbert space, we just saw that all measurements are controlled by the reduced density matrix. But when you compute the reduced density matrix, in that case, you get something that is proportional to the identity. And that's literally a random bit from the perspective of a subsystem. So that's a little bit the slogan that sometimes entanglement gets attached, which is that entanglement is the quantum property that allows someone that has access to the full composite system to know everything that there is to be known about the system. But if you only have access to a subsystem, you can be maximally ignorant, as this case here. Notice that this doesn't happen classically. If I give you a code and I divide it into 2, you can access as much information about the piece of paper that you are given as a subsystem. That's not true for entangled states in quantum mechanics. This discussion is much more general, and obviously I will run out of time as expected, but I just wanted to convey that if I compute the von Neumann entropy of what physicists call a thermal state, like in Diego's talk, we are given this ensemble in that case. That's Boltzmann thermal canonical ensemble. It's that's the answer. And if I compute the von Neumann entropy just as an exercise, as an example for this lecture, since rho beta is already diagonalized in the eigenbasis of the Hamiltonian as written here, when I compute that formula, I get 2 contributions. I think that here I forgot a beta, apologies. So the point of this wrong formula, apologies for that, is that the von Neumann entropy reproduces the thermodynamic entropy of thermal states in quantum statistical mechanics. The piece from the average energy comes from the log of this exponential, and the piece from the free energy comes from the normalization. And since I may run out of time, but perhaps I should stress this, anytime that you have some mixed state, like the canonical ensemble here, there is some uncertainty. We just computed it, the Neumann entropy, which equals the thermodynamic entropy in quantum statistical mechanics. There is a process that allows you to purify this mixed state. And the easiest way to do this is to include a second copy of the Hilbert space that we were discussing up here. So now I have two copies. And I basically take the square root of these probabilities that appear here. So notice that the coefficients that appear in this pure state, now this is a vector, are the square roots of the coefficient determining the probability a la Boltzmann. This is the square root of the exponential and the square root of the partition function. So this vector is not uniquely defined, I have to say that, but if you compute the density, the reduced density metrics of this one, you get the thermal state. And if I have time to talk about gravitational physics, you will see this emerging in a few minutes. Okay, so just to make one. Sorry?
5 minutes.
Okay, wow. So now I need some whiskey to accelerate, but okay, it was clear that this would happen. So what have we learned? So we have learned that the notion of ensembles in quantum mechanics is described by density operators. And one natural way to come up with these systems is by coarse-graining. And coarse-graining in quantum mechanics means tracing out a Hilbert space. And the natural notion of quantum information is accessible through measurements. Now, the issue of locality shows up in the following way. So Feynman taught us that if I want to compute the probability that a particle x1 at time t1 propagates to a position x2 at time t2, quantum mechanically I need to compute this transition amplitude. Here I'm using this notation for the position of the particles and the eigenvectors. But the point that I'm trying to convey is that there is a classical formulation of this quantum mechanical amplitude calculation in terms of summing over all possible paths. These are classical objects at this point with some measure, which it's the hard part, and weighting each weight with the classical actions that Diego was using to compute his geodesics in his talk. So that's one of the many contributions that Feynman had. We can ask, is there a way of representing the wave function of the vacuum using path integrals? The answer is yes. If you do a big rotation as Diego was doing, if you take the limit of the Euclidean time going to infinity, what happens in Euclidean time is that energies get damped, as you can see in this formula. Sorry for rushing. But the statement is that if I take the Euclidean time to infinity, I get something that up to some complex phase reproduces the wave function of the vacuum. Now, imagine that I give you a collection of Hilbert spaces. Let's think about spins. These spins are located somewhere in the plane. The notion of entanglement is always associated with factorization of some Hilbert space. And now I want to talk about factorization in real space. So, such as the lattice that you are seeing here. So if I divide my system into Alice Hilbert space, which is this sphere, and the complementary, which is all the spins outside of that circle, if you compute the entanglement entropy, what you will get is up to coefficients. The dominant contribution goes with the area of this circle. That's the statement. And if I go to quantum field theory, I have exactly the same picture, but the difference is that instead of having a finite number of outcomes at each point in this lattice site, now I have an infinite number of values, which is the value of the field at the location of the lattice point x. That's the object that appears naturally and diagonalizes the operator field in quantum field theory. And the intuitive picture that I wanted to convey is that the vacuum, which is the state that minimizes whatever Hamiltonian you are studying, can be written as a linear superposition of these eigenstates, the eigenstates of the operator field. So the vacuum looks like a very complicated linear superposition, and you shouldn't be surprised that the vacuum has non-trivial entanglement with respect to factorization in real space. That's the reason why I went over this discussion. Now, the Feynman picture in quantum field theory can be extended using path integral. So we can ask the question, if I give you some state in some field configuration phi1, and I want to compute the transition amplitude to phi2, how can I do that by Euclidean time evolution? Well, I extend Feynman's quantum mechanical rule to path integrals in field theory. Now I have a measure over the space of field configurations. I have the action that Diego wrote down before taking the WKB approximation. And in terms of pictures, what I have is my initial state determining some configuration. This is this red line, the final one, and then I have some evolution. What I have to sum in between is all possible configuration connecting both configurations. If my field theory is not on the real line but on a circle, then this looks like a cylinder. What about the wave function? Well, the wave function can be viewed as some functional, such that if I give you the data of the bra, it gives me a complex number. So one way of thinking about it, heuristically at least, is let's take the path integral that was defined in the transition amplitude, and let's leave the upper boundary of my path integral undefined. This is some formal object, but it definitely satisfies that if you provide me with this ket, I will obtain the transition amplitude. So whenever I draw these pictures with no initial or final data, I'm referring to these formal functionals. And this calls for the density matrix. In this case, I have a cat in the initial state and a cat in the final state, and that defines my density matrix formally. And the thermal partition function is taking the trace of the evolution operator. And taking the trace means, in this language, summing over all configurations. But summing over all configurations is taking the cylinder and gluing them. So the end result is the torus that basically appears in all discussions in this topic. Let me try to finish with this, because and I will not mention anything else. What I really wanted to ask is the following question. So now I give you some field theory in 2 dimensions. Time is vertical and space is horizontal. And I want to ask the question whether it is possible to define a subsystem for a subset of observers, which are these red trajectories, which are confined in some subregion of my space. It turns out that if you ask what is the trajectory of a constantly accelerated observer in Minkowski space, they are confined in this right wedge. Now, it's interesting to compare those non-inertial observers with the inertial ones, which are these blue guys. Because if the blue guys are carrying some lantern and they try to send light, these are the green lights. You see that as soon as the blue dots cross this black boundary, the light will never be perceived by this accelerated observer. So technically, we say that the accelerated observer sees a horizon. And whatever amount of information is encoded in this light is lost from the perspective of the accelerated observer. So we want to ask the question, is there any entropy, is there any uncertainty associated with the description of an accelerated observer? And the answer will turn out to be yes. What I want to do is I want to take the vacuum of my field theory. This is the density operator. And I want to trace over the left-hand side, because this is the part of the Hilbert space in the factorization in real space, which I don't have access if I am an accelerated observer in the right-hand side. So I want to compute this reduced density matrix in quantum field theory in Euclidean signature. So this is my last thing that I want to say before shocking you with the answer. So the matrix elements of this reduced density matrix are specifying the state in the right wedge. So this is phi1 and phi2. And to compute the reduced density metrics, I need to sum over all the possible configurations that I will never see as an observer in the right-hand side. So I'm summing over the phi tildes. Summing over the phi tildes means that I'm gluing this piece of the path integral. And the trick to interpret physically the answer is that if instead of using Cartesian coordinates, I re-slice the path integral in polar coordinates, the transition amplitude that computes this matrix element can be understood as the action of the rotation operator generating a Euclidean time evolution in the polar angle phi. So more for the people more mathematically oriented, I'm introducing a Hamiltonian, which I will call H. Rindler. This is what Bartek did almost immediately in his talk, which generates time translations, Euclidean time translations, through this commutation relation. The claim is that the reduced density matrix is the exponential of this Hamiltonian. That's the modular Hamiltonian Bartek's talk. But this looks like a Boltzmann factor in our quantum statistical mechanics example, and indeed it is. When I go to Lorentzian signature, the physics associated with these accelerated observers are encoded in this with this non-trivial temperature, which involves all the constants in our system. So since this is all I wanted to say, if I use the equivalence principle, you may suspect that this has something to do with black holes, but I don't have time for that. So I just want to close by stressing what I said at the beginning, which is the details of the Unruh discussion are obviously very different from the discussion concerning a simple qubit system in quantum mechanics, obviously. But in terms of very abstract terms of what is the accessible information that accelerated observers have, and someone has between two labs that are very far away, in terms of information theory, the problems are very similar. Therefore, the mathematics are similar, except for the path integrals and all these details. And indeed, the Unruh effect can be explained in this way. And this has consequences for gravitational physics, which sadly I didn't have time to cover. Thanks for your attention, and sorry for not succeeding in explaining everything I wanted. Sorry.
Thanks, Joan. Other questions?
I have a question, Joan. Hi, this is George.
Hi, George.
It's a nice talk, and so in this discussion, locality is very important, right? Apart from information, right? Locality.
You are completely right. Yeah.
So locality, the way you would think about it, is just simply classical locality, right? Defined with respect to classical space-time. How would you define locality in a more intrinsically quantum way?
Well, as you know, this is a very hard problem. Okay, so actually, okay, I don't have an answer to your question, to be fully honest, but I was trying to touch upon this in the following way. So let me tackle your question in a more technical way. So imagine that I am someone interested in gravitational physics, and I'm coming from GR. The question of locality is, even if I look at it classically, so even if I worry about your deep question, which is much deeper than what I'm going to say, already at a classical level, if I try to play the same discussion as in field theory, meaning I take a Cauchy slice and I define my state in that slice, because of diffeomorphism invariance, the Hilbert space does not factorize. So there is this huge elephant in the discussion, which is also true in electromagnetism, as I'm trying to remind here. So what I find fascinating, and this was a little bit the speculative part of the talk, is that in electromagnetism you are not forced to, but you can understand the notion of locality in electromagnetism in terms of H modes.
Yeah.
If you like that story, which you are not forced to take, every physicist may take its own take on this. But if you like that mathematical exposition of things, the question that I've been interested recently is whether there is a notion of H modes in gravity, because even classically, I have to answer that question. And the speculative part of the talk has to do with this picture here. So if I take the wormhole that appears in the classical black hole, I am told that the area that appears in the first law, which I can interpret as in EPR equals ER, but all this is kind of a standard, but it doesn't answer your question, George, as you know. What I'm trying to understand is whether these are all ideas by Susskind and Uglum, which are a little bit vague in my mind, but of course extremely interesting conceptually, whether there is some open-close string duality, on the wall sheet when we are in Euclidean signature, as you were highlighting to Diego. We believe the ADS-CFT very secretly has to do with the fact that I can view at this picture in the left as a closed string propagating through the right, or I can look at it as taking an open string and having a one loop. And then you have some boundary condition here, which defines the D-brane and all sorts of so forth. So it's quite fascinating that, I've been reminded recently that in the so-called, this is only for experts, apologies, in the so-called Oguri-Strominger-Baffa conjecture and in topological strings, there are large N dualities proven on the wall sheet, where whenever you try to do bulk physics, you are basically trying to answer what you were asking to Diego in terms of when you go to a Euclidean signature, there is some choice of what you call Lorentzian Hamiltonian. You could either take the standard clock of the black hole, or you could take the radial direction. From the Euclidean perspective, you couldn't care less. But of course, the Lorentzian evolution is different. But that's precisely what in the wall sheet we are doing. You are exchanging the role of the tau Hamiltonian with the sigma Hamiltonian. And in the case of topological strings, Oguri and Baffa actually claim to have made sense of this. And so one of the things that I've been trying to see, I'm not answering your question, George, I apologize, but is whether there is an open string picture of the closed string physics that gives you the black hole entropy in ADS-CFT2 using Chern-Simons theory. Because in Chern-Simons theory, the H modes, our friends in condensed matter do understand H modes. So I'm trying to rephrase a little bit a la Berlinde, the Witten description of 3D gravity with negative cosmological constant using those H modes. But I don't have anything terribly successful to report yet, but yeah. So,
okay, well, thank you. Thank you for telling me about this.
Thank you for asking and giving me the opportunity to mention it. Sorry.
Okay, great.
I owe you a beer.
Okay.
Any other questions?